Good day, sir. My name is Johnson Lee Chong, and today I'm going to present to you the lab 5, which is the effect of different PID value. So first off, we go to the procedure 3.1.1. So with 3.1.1, without the PID controller, you can see that our system rest time is 2.59, the system transient time is 4.6, and the final value is 0.5. So all of this value, except from the final value, will be put inside the table. So with PID control, so when the Kp is increased and while Ki and Kd is constant, we can see that the graph will be moved like this. So if the Ki is increased while Kp and Kd is constant, the graph will be like this. So, and when the Kd is increased while Kb and Ki is constant, the graph will be like this. So for the table 3.1.2, as I said just now, all of the value will be included inside the table. So for without the PID control, you can see that the rise time is 2.59 and the setting time is 4.6. So with PID controller, we can see that the Kp is 10, the Ki is 1, and the Kd is 1, as we can see inside this table. So the value is given as this. So when the Kb is 15, the Ki and Kd is 1, this means the Kp is increased only. So the value is given like this. So for the second condition, when the Ki is increased while Kp and Kd is constant, so which means when the Ki is increasing only, which means that this one, the number 3 one, is increasing. I'm so sorry. So the value will be given as this. So if the Ki is 7, which means the value will be like this. So for the third condition, when Kd is increased while the other two is constant, which means the Kd, the S square value will be increasing. So the value will be like this. So if the Kd is equal to 5, the value will be like this. So for the second part, this is the calculation to be shown. After we calculate the xs is equal to 1 per s square plus bs plus k, we can substitute the value into the gs to find the value of gs. So for the graph 4.1, so this is the graph without the PID controller, and this is the graph with the PID controller. So for the procedure 3.2, as we can see, without the PID controller, the value will be like this. So with the PID controller, when the Kp is 300, that means the upper side, and the K1 is 0 and the Kd is 0, we can see that the value will be like this. By the way, all the value, if want to be referenced, we can see at here. Okay, for the second one, when the Kp is 300 and the K1 is equal to 10, which is at here, the value will be like this. So if the Ki is equal to 0 and the Kd equal to 50, the Kp is equal to 305, the value will be like this. For the fourth part, when the Kp is 350, the Ki is equal to 300 and the Kd is equal to 50, the value will be like this. So this is the end. Let's continue the discussion. So the most important part for the PID control system to be functioning or to be constructed is to have the proportional, integral, and derivative response. The more the value, the proportional gain Kc speed up, the system respond to the error signal, but they also increase the risk of oscillation and instability. So if we continue to modify the output, the integral component effectively will reduce the steady state error by building out the error factor over time. But Integral wind up, which happens when saturation prevents the error signal from going to zero, is problematic. So when we tune it properly, the derivative response increases the system responsivity. However, with higher derivative time, which is TD value, it's become more susceptible to applying noise and instability. The derivative response is sensitive to the rate of change of the error signal. So in order to achieve desired control system performance without introducing instability or excessive oscillation, it is imperative to achieve an optimal balance between these parameters. In conclusion, to perform the best possible system performance in the domain of PID control, which is the main reason why we do the lab 5, the proportional integral and derivative parameter must be adjusted. The interaction of this element will produce a fine balance between the responsive and stability of the system. A trade-off exists while adjusting P, I, and D value. The larger interval value minimize steady state error but integral wind up, while increasing the proportional gain improve response speed but increase the risk of instability. Elevate derivative time value improve responsiveness to abrupt shifts, but they may also intensify noise and cause instability in the system. A thorough observation of the system behavior is required for the iterative tuning process, which is unique to the system characteristics. This emphasizes how crucial it is to comprehend system dynamic in order to develop an ideal control strategy. In the end, PID control is still a reliable technique, but it requires careful parameter adjustment to find the ideal balance for efficient control while taking the unique characteristic of the system and the trade-off between responsiveness and stability into account. So that's all from me. Thank you, sir.